Hello, am I audible?
Yes, you are.
So we are starting our program of today.
Is sir is there?
Learn is a yes.
Is sir is there?
Is sir there?
He has not joined, I think.
Have you checked the photo?
No, he is not there. Still now he has not joined.
He has not joined.
He has not joined. Okay. For the same starting.
That's 5 minutes. He has not joined.
Okay.
So,
Open for 5 minutes. So we have to wait for 5 minutes and then we will start.
yes, he has joined. He has joined. Okay.
Okay, ma'am. Okay.
The capacity to learn is a gift. The ability to learn is a skill. The willingness to learn is a choice. So good afternoon, all of you. Final day of the IUC International Faculty Development Program, organized by B.T. Poddar Institute of Management and Technology. Our speaker is Dr. Kallol Mallick, founder and CEO of Azure Software. He will deliver a lecture on signal and image processing, a journey through ages. Mr. Kallol Mallick, Assistant Professor of Electrical Engineering Department, to introduce our honorable speaker.
Orgo, you have to unmute your microphone. Orgo, you have to unmute your microphone. Orgo, just unmute your microphone.
Okay, I'm done with it. Okay.
A very good afternoon to all of you. It is my huge privilege to welcome Dr. Kallol Mallick here on the fifth and final day of our FDP. Dr. Kallol Mallick holds a BTech degree in Computer Science from Indian Institute of Technology, Kharagpur, and a graduate diploma in Advanced and Parallel Computing from Santa Clara University, California, USA. He is the Doctor of Philosophy in Computer Science from Indian Institute of Technology, Kharagpur. His research includes image processing and video compression in low-power embedded systems. He has over 25 years of experience in data analytics system with emphasis on real-time data and image or video. As founder and CEO of Azure Software Private Limited, he leads the team to design and develop AI/ML-based analytics platform for machine-generated high-speed data and spatial analytics using image and videos. Azure also has extensive expertise in embedded system software, data capture, statistical analytics, visualization leading to its IoT domain applications in defense, healthcare, and industrial automation. Prior to joining Azure, Kallol was principal architect of fiber channel storage products at American Megatrends Inc. USA. He was instrumental in guiding a group of engineers to develop fourth generation of storage and SAM firmware and management tools. Adjunct Professor, Center of Excellence in Artificial Intelligence, IIT Kharagpur courses on AI/ML for image and video processing, research projects in sensor, image and video. So here, may I request Dr. Mallick sir to start the session with his topic entitled Signal and Image Processing, a Journey Through Ages.
Hello. Thank you. Am I audible here? Am I audible here?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay.
You are audible.
Thank you. So,
Absolutely audible.
yeah, let me start the presentation here.
Before sir presentation, I will request everyone to please turn off your camera and microphone. Yes, sir, it is visible.
It is visible, right?
Yes, sir, it is visible, sir. Absolutely.
Great. So we will talk about the signal and image processing. As you know that it has started for quite some time more. Then it just started what happened earlier and where are we, and then we'll look forward from that point with that background in mind, that where we are heading, what is the direction where our research and all the studies should be directed, and to keep up with the world. So what I did was that I tried to go in the chronological order. I have divided it into 4 sections. The first section we will talk about a little bit of history, 60s, 80s, initial days of signal and analog to digital communication, etc. Then I will go through the image processing stuff, a little bit about it, and mainly on the compression what the thing that has happened at that time, and then we look at what was happening on the ancillary technology, like the communication, bandwidth, processors, storage, all these things that are required for a user experience with image processing applications. And lastly, that is the most important, and probably that will take the longest time. We will talk about image processing and artificial intelligence and how it is spanning out today, what are the technologies that are available, and where we are heading to. So this is, I'm assuming that you guys have, most of you have worked on it or have experience on it. So I didn't try to go more into the theory or anything like that, but try to see it from the application point of view, try to see the insight that we can get from here, and see how that can help us in deciding what we are doing right now. So our section here starts with a history. Let's see what is a signal. Any time varying waveform, as per the definition goes, is a signal. Now, when a signal is not always is electrical, it can be anything like when I'm talking to you guys. Actually, if I talk face to face, it's a sound signal that is going to you. Right now, the sound signal is getting converted in different waveforms, and then ultimately you are again getting a sound signal. So talking and listening is passing a signal. Even gesture and expression of face, all these things are different kind of signals. Through our body, the neurons, the hormones, everything sends some signals from one part of the body to other. In the non-living area, we have audio, optical, electromagnetic, thermal, different kind of signals happening in different way. So even a Morse code is a signal. When the cricket umpire shows a no ball or a white ball, that signal can be in different form in different ways. For us, what is important is that to note is that that signal carries some information. We will be mostly interested with the information part of it, and we need to preserve that information. So in that way, to handle with that information, we can transform the signal to different form, but we need to keep in mind that the information should not be eroded in that process. So, for example, audio to electrical transformation, when I'm talking to a microphone, transfer to an electrical signal, and then if it is going over a fiber channel, it is again getting transformed to an optical signal. And we all know that we have done time domain, frequency domain, just for our sake. The signal remains the same, that the representation changes. So with the signal, these are the signal processing operations we primarily do: the transformation and transmit from one point to another. That may be across the world, that may be within an IC, but it's a transmission and communication in all the sense. Then we also store and retrieve the signals, and then comes the searching, sorting, and keeping some tag with those things. And lastly, and the most important thing that we need to do is that we need to interpret the signal, what it means, what it tries to convey, and we need to extract the information out of it so that we can take some action based on that. When we are talking about signal processing, what we do initially is that the only form that we handle out here is electrical signals. So any form of signal, be it sound, be it light waves, whatever, we convert it first to electrical signal. Then in recent times, earlier we used to work with analog signals a lot, but recent times we always convert it to a digital format, where we have only the information content in forms of bits and bytes. So this is the flow of any signal when it is handled through. The basic signal processing steps, assuming that it's an electrical signal, usually we have a low pass filter to clear up some errors, transmission errors or acquisition errors that we creep in. Sample and hold circuit then converts it to a digital format. So here we are seeing the waveforms, the waveform that is getting changed when it travels from source to destination. Then we have some kind of ADC, analog to digital converter, some digital signal processing, which does something on the thing. It may compress, it may do error correction, it may do whatever it wants to do, and then again it converts to the analog, to a DAC card. Because when some action has to be taken, either it has to be seen or heard by a human, or some machine has to take it. Every action has to be through analog, because nature works through analog signals. So we have to again convert back to analog. So this is a typical flow of a signal processing. We'll start with the digital era of the signal. The analog signals were there earlier. So it starts with the logician and the engineer. There is a famous book by this name, by Paul Genahin. The logician is Boole, after whom the Boolean logic is named. And this is a quote I think is very appropriate for Boole and Shannon. Shannon is the scientist who, or should we call him engineer, who has made this into practice. So it says that it is because of Shannon that Boole is rightly famous today, and it is because of Boole that Shannon first gained the attention of scientific community. The year of miracles. In every field, we see that usually there is 1 year, 1 or 2 years when a lot of things happens. The direction of the field changes years after that. So, for example, in 1666, the Newton's laws, Newton's discovery, and discovery of calculus has changed the mechanics part of the physics altogether. Similarly, in 1905, Einstein's discovery has changed physics like that. So, if we have to find out a year of miracle, that would be 1948, when Claude Shannon wrote this paper, The Mathematical Theory of Communication. So what he did was that he took the analog communication, converted to digital, and formulated the mathematical basis for this based on the logic, the mathematics which has been formulated by Boole. So there are 3 things he has pointed out in his paper. One is the digital circuit. He shown that the Boolean logic can be implemented in electronic circuits. Then second is the digitization. The analog signal can be transformed into bits, and then bits can be transferred. Bits can be transmitted from one end to the another, and if there is some error, that error can be connected. He created a model of a channel. We'll linger on with Shannon a little bit more to understand exactly what it meant. So the way I would like to, it is more like a discussion kind of thing. So if anybody of you want to interact and go to a discussion, want to discuss, we can be open for that. So to interrupt me whenever you think. So the Shannon's paper, if you look at the content, the chapters in this, that itself shows that how important this paper was in the history of signal processing. I would request all of you, it is even easily available, freely available on internet. I will request all of you who has an interest of working on this, go through it not once, at least twice or thrice, to understand exactly what he meant. There are a lot of insights in this paper, and it's written so simply that it is very easy to understand. So this is the transmission model that Shannon has created. It starts with the information source, and it sends some kind of a message to a transmitter. Transmitter sends the signal and there is a noise source. He assumed that there will be a noise over the received signal is received by the receiver. The receiver then sends it out to the uh, destination. So it's a very simple model that he has created, and then he created all his theories based on this. The first thing is that he has created the mathematical model for the channel, and he has developed this choice, uncertainty, and entropy, where he measured the information content in a message and how to measure it. And he has also proposed this fundamental theorem of noiseless system, showing that, proving that the maximum transmission rate can be C by H. So this way he created the mathematical basis for efficient encoding and decoding. What is the maximum best possible encoding decoding that is possible on a channel if it is noisy and if it is noiseless. So noisy channel also he has defined the limit, what limit can be reached when a source which is X is transmitted and what signal Y is received, assuming that uh, there may be noise in the channel and 0 may get changed to 1 or 1 may get changed to 0. So he has defined what is the mathematical basis, what is the maximum bit rate that we can achieve. So in the earlier days when all this started, it's very exciting to see that how at that time the engineers approached that. So here Anders Robinson, he has some very pioneering work in radar systems. So he out here recollects that in the very beginning he got some seismic data and how we converted it to a digital data by hand using a t-square and scale. So just reading it on a graph and then putting the numerical values. So it all started like that at that time. Everybody was working on this crude way, and then all this sophistication came one after another. Some of the works that we have listed here, and some of the institutions who have a great influence on the history of signal processing, how it evolved. So if you look at the series, all 60s, 70s, one of them are in 50s, it talks about threshold signal. Then we can see Reed Solomon signal, error correcting signal, that is again 60s. And the fast calculation for Fourier transform, which was a must for having it done on a processor. Otherwise, the calculation was so lengthy that the processor could not cope up with that speed. So that is again in 65. Look at this. This is mostly at the time. And if you look at today's work also, a lot of the work is based on the theories that has developed during 40s, 50s, and 60s. For example, these neural nets that everybody is hoping that it will bring miracle to the processing world. So that neural net was actually developed in 1940. We'll come to a more detailed discussion on neural nets later on. The institutions, mostly the US universities and Bell Labs and AT&T Labs. So these are the places where most of the innovation has happened. And at the time, the industry like MIT and Stanford worked very closely hand in hand with Bell Labs. That is one of the things that we should look for in our country also, because I feel that in our country we have that lack of coordination between the labs of the industry and the educational institutes. So that it has again shows that whenever this kind of collaboration happened between the industry and the research, then wonderful things happened. Then there are a bunch of companies who are primarily chip maker companies. So they directed their R&D on the development of the chip, development of the processors, development of digital signal processor chips. So among them, Texas Instruments, Intel, Motorola are pioneer. NIC also have contributed quite a lot. And lastly, whenever a theory, a process is developed, that has to be ultimately put into use, and there has to be some application where the people are using it. So for that, Philips, JVC, and Sony, they have put all these processors, all these processing capabilities into devices which are have used in their daily life, other the industrial applications. So step by step, if we look at the 50s, 60s, and 70s, I will not go into the details here. I will just give the overview. That initially we have these tape recorders where everything was stored in a magnetic tape. Then slowly it has converted to CDs, DVDs, and if you the 70s also we have seen the mix of magnetic storage and also some digital storage started coming in. So this 50s, 60s, and 70s are primarily, if you look at this, there are two main areas where the work was going on. One of them was the telephone, the audio signals, how people talk with each other, how easy that can be, what is the bandwidth, and the second thing that was going on was mainly on the TV area, where people TV and radio era, where some broadcasting event has to be seen or heard by people everywhere. So these are the mainly two areas where main uh, development was happening. Coming to the 80s, we have seen at this point that a lot of processing power, people have felt, the companies have felt that the processing power is lacking for the application they are looking for, and so a lot of investment has happened on the processing power. Some of the signal processing chips on the second column that we see here are quite famous. That TI's TMS 22010 DSP chip was quite famous at the time. Early 80s, on 82, the parallel computing also started slowly. This DSP32, what came in 1934 by AT&T, we also see some variants of this still today. Motorola 5600 was also quite famous. It was put into their Motorola handset later on. And the workhorse for all embedded system was Intel i860. It started with Intel i860. Then they came up with 960, and 960 was there. I think till late part of 90s, 98, 99. There were different series version, and I actually happened to work with Intel i960 earlier. And after that it was converted to 1060, and then we have seen the other processors like PowerPC and the Pentium brand coming into the embedded system group. On the computing power itself, we can see that in 1981, first we have seen the IBM PC with the DOS operating system, and Apple Macintosh came at 84. First version of Microsoft Windows was 85. Though I think the first version that we have seen in India was late 90s, probably mid or late 90s. On the application side, this is voice, CD player by Philips and Sony, and different kind of consumer thing for video games, Walkman, CD, all these things were there, and those things were pushed by mainly from the Japanese company. So this is a look back to the history, how 1980s used to look like. So how many of you have seen those devices? People who are born in 70s or early 80s have seen tape recorder probably. This cassette type of VCP VCR, they have probably seen. Yeah, Rubik's cube was also invented during that time, and India won the World Cup. So that we all remember. So these are the some of the images in the 80s. This is just to give for young people who did not see what was there, just to give a visual impression how it looked like. 80s and 90s, a lot of things happened on the image processing stuff. So in 80s, the still image compression standard on JPEG came up, and the video compression standard first version of MPEG came up in the 90s. And what was originally developed in 1940s, the neural network. Some application of neural network, people got interested. People try to work on it. Actually, what happened was that after 1940 or when it was invented, it was very much in the vogue till 50s, 60s, or part 70s. After that, people think that it is something that cannot be used because it used to take long time for computation on the standard processors. So they thought that neural net was a nice idea, but it is not a practical thing. So it was kind of shelved. During 90s, again, the people got interested on the old thing and saw that probably it's time where we can work with neural nets. So before getting more into the JPEG, MPEG, and how it happened, let us go a little bit on the image processing. Let us introduce image processing. What are the image processing stuff that we do? Again, we will try to cover more on the application side rather than the theories and processes. So, anybody want to comment, want to discuss anything out here before we go into the next?
No, sir. As such, there are no questions yet. You can
Okay.
proceed further.
Yeah. Okay. Thank you. Okay. So let us see what image processing means. Some of these works are. This is again when I talk about image processing. Some of these works has been done a long back. Some of them are still we are working on this. Some problems has been resolved almost completely. Some are not yet. So these are all mix of things out here. So here we can see that signal processing is actually the big subject, and specialization of that is image processing, and again within image processing, video processing is that another specialization. So what I wanted to show out here is that when we call a signal, we usually mean those signal means everything. We usually means it's a spatial signal. This is only one value, one scalar value which is going up and down, and it's temporal. So it is a function of t only. And when we talk about image, a still image, it is a two-dimensional. It is a planar thing, and usually it does not move with time. So it's a still image. And video, we have two spatial dimension, and then it has a time dimension as well. But again, in today's world, an image can be a 3D image, a video can be a 3D video, a holographic video, and a signal can be a vector signal also. So this is primarily what people think when we think about the signal or image and the video, but obviously this is not absolutely correct in the true sense, but it is what the notion is. So steps in image processing, what do? We have to first do an acquisition of the image. So either through a camera or some kind of devices, we have to capture the image, we have to store it somewhere. Then we do some kind of pre-processing. Whenever we capture an image that may not be of optimal quality, so we may have to do some enhancement, and or we can We can crop it, we can remove some portion of it which we think is not required. And the second, after that, once we do the pre-processing, so after that we can either transmit it, store it, or if we want to interpret something from it, we do some feature extraction to understand what the image says. When I say feature extraction, it means that it will try to identify what kind of color is there, what kind of object is there. It may be some object. Maybe I may be interested in matching this picture with somebody else. So it may be something like a face recognition kind of thing. I take a picture and then match with my database, or it may be just writing a description for it. This is the kind of work that is being done recently. Quite a long people are interested and to have an automated description. And then also what we need to do is that once we do that, we then understand what the image is about, what is the semantic of it. So the object detection and tagging and classification, what it is. This is a cat or a mouse or a flower or a human. What are the things that, what are the objects that are there and what they're doing. So more or less chronological. People in the very beginning were with how to capture an image properly. So 60s and 70s mostly on the cameras, different kind of cameras, and then ultimately we are now having the digital sensors. So the initial it has happened like how to acquire an image. Then we have seen a lot of algorithm being developed on 80s and 90s. At the time, once we have an image, we try to process it, we try to improve the quality of it, and we also try to see how it can be preserved for a longer time. Like if you look at the old pictures taken by a camera that get bad, the quality get bad. Let's say after 2000, most of the things people are trying to do is that trying to deploy artificial intelligence and machine learning stuff to understand what the image means. This is interesting. This is the first photograph in 1826. So a person called Joseph in France, he used to work with lithography. He took this first photograph. It is on what it's called the bitumen of Judea. That's a chemical, that is a photosensitive chemical. So he has applied it on a metal plate and then exposed it to sun. And what it says is that roughly, if you look carefully, on the left side and the right side, you will see the images. I would rather say that shadows, not the images. It's some shadows of some building. So it's a view in front of his portico, if his house is portico. So this is the first photograph. Now imagine we started from this kind of quality of image and where we are today. Now jump to the different kind of images that we see, that we work with. There are some remote sensing images. It is from Indian Institute of Remote Sensing. It shows aerial image from where it shows the flooding along Ganga River in Bihar. The next picture is that India's picture captured from Mars surface from Mongolian. It is from ISRO side. So these are the when we saw when I talk about image means all these images also. So it's not only the image from a camera, but it means all these things. On the right side, we see some medical images and USG, X-ray, and all these things. It can be a scan of a document also, and various other type of images. What are the objectives? What do we want to do with the images? Our objectives are, we first enhance perception. Image is a reflection of reality. The reaction that is stored, that is measured and kept. Uh, so the first objective is that enhance our perception about the reality of which the image we are seeing. Second thing is that identification of the object. Like looking at the image, we should identify what it is and what it wants to say, if it contains any other information, etc. On image processing, we also would like to understand the structure and geometric detection. So looking at a building, we should be able to find out that how high is the building, how far it is from the cameraman, what is the shape of the building, whether it's a rectangle or a round shape in the front, and the position, role, interaction with other objects. Like if we see a picture of different people doing something, we need to understand whether they are quarreling or they are playing a football. So we need to understand that. Now, all these objectives are very easy when the other end, we human are seeing it. So all these things are happening in our brain, and it is happening so fast and so naturally that we don't identify that we are doing these things separately. But when it comes to image processing, we need to resolve each of these problem one after another, and have a bunch of studies, bunch of research going on in each of these things. What are the operations that we do on the image processing? We have covered a little bit of this, but on signal processing side, but specifically for the image processing, we do transformations. We do develop some models of the images such that we can enhance and do some processing on that. We develop some filters for the images for restoration and enhancement. And since image files are quite huge, so we have to compress it either to store it or to transmit it. And then we also want to do reconstruction. These are the primary things that we do on image processing. And again, when I talk about image processing OTR, it is mostly still images. On video, we have a couple of things more that we also need to do. We'll come to that again. On the application area, these are the list of applications that are typically important in today's world. So the consumer application, OCR, photography, video conference, all these things are very important. In computer vision, a lot of people are moving towards robotics. Criminal and surveillance at this point is very important. Medical imaging SAR, and digital astronomy images from space. So this is again something that everybody is excited about, especially the research community is very excited about processing the astronomical images. So let's see some examples. When I say structure recovery, what we want to do. You see the picture of two buildings from two different angles. Now, what we need to do is that we need to identify a 3D geometry of this building from these two flat pictures. So what we have to do, we have to find out the camera perspective that we have tried to show on the two sides, on the lower side, on the left and right side, how the cameras are positioned, and we need to find out the binocular vision, and then we can identify the 3D nature of this. This is something which has been used recently when the fire broke out in France in one of their famous churches, the Church of Notre Dame, and the top thing has broken apart. At that point, they had a lot of pictures like this from tourists and from different places. So they used this kind of structure recovery image processing to make a 3D model of the structure, and then created that structure as it was earlier. This is a typical image enhancement example, where if you take a picture from the top, aerial picture, the somewhere near Sundarbans will look something like this. But we can use image processing to enhance it. Very simple things like contrast and brightness control and all these things can improve a lot. But other than that, there are many other sophisticated methods for enhancement of the images. Again, this is a application where with aerial photography, where an institute or a government can take a aerial scan of an area and then find out what is where. So out here we try to identify that where the road goes, where is the green vegetation, and where is the concrete, where is the vegetation that has gone dry. So it helps there in city planning, urban planning, and also for surveillance. Now the images that we have seen so far, all of them are 3D images. That means they are images of some object which are real life objects and they occupy some 3D space. Here, this is the image of our chromosomes. So they form a planar kind of image. Though they are 3D itself, but they are a slice in a microscope and they form a planar kind of images. The karyotyping is the image processing technology where we need to identify from these chromosomes to identify what the exact chromosomes. So you can see that on the right side, it has tried to identify the pairs of chromosomes, which values where. And lastly, the images from the space. Now, encoding, reconstruction, and enhancement of application are done in the space. So these are the few dates where we as a human have got different images from foreigner. The left bottom side, the image that you see where the colored images are, the image that you see in the center, that is the image we usually see on TV and internet and everywhere else. But these are the different component images that are shown separately, and it is image processing task where these components from different wave range is combined together and to form the image that is there in the center. Again, on the top right, on the picture of Mercury, which looks more like a black and white picture. So if you look carefully out there, you will see that it is a mosaic picture. Mosaic picture means there are different small pictures, and then there are some corrections of stitching those small pictures to create a bigger picture. So you can see some square blockiness in that picture if you take a closer look. So early works on image processing. There are some books that are available on 70s, which were very famous books. And basis of all these things, we have the tools for thresholding, the O2 thresholding gradient operators, and then we have the transformations like Fourier transformation, KLT, DCT, and discrete Fourier DFT, and all these things. Just to give you an example how it works, the filters and gradient operations using a mask. So we have two simple operators, the Prewitt operator and Sobel operator. So you can see that they're using the Sobel operator, how the lines, the vertical and horizontal line gets picked up, gets accentuated. And what we knew at the time is that this kind of filter and convolution, what was a tool that we use extensively even today. That is mathematically the same process, but just done differently. So that is what is shown out here. This is an example of noise filtering. I'm just giving some example of what kind of pre-processing and what processing is done. All these things are so far are algorithmic. There is no AI. These are all deterministic things. And let's come to the compression. I like this slide very much because it gives us a idea of why DCT kind of thing or a transformation like that is useful. So what it says is that the upper squares in the 16 block squares on the upper row is the basis image. So everybody knows about that. And if you look at that, it follows the pattern. And the lower bottom is that if I have a weight of 1, 3, 2, 4 as shown in the picture, just randomly picked up, then I can create a block like this from the basis images. So a 16 uh, block uh, 16 block area of image can be represented using only 4 numbers, 1, 3, 2, 4. If the sender side and the receiver side both know what is the basis image. So that is the idea behind all the compression algorithms. On that compression algorithm, the what is used primarily is that discrete cosine transform DCT, and that is on a picture we have shown that how that works lower below. So on the left hand side is the original image of Lena, and then we have divided the image into channels, the Y, CB, and CR. So Y is the luminance, CB, and CR the chrominance block. And then taking only the Y block, we have calculated the DCT, and the DCT coefficients are just shown on the blue channel, just for to give it an representation. And then if we reconstruct this image, what is the image that we get? So this is the process of converting it to DCT and then reconstructing from that. A JPEG with this background, a JPEG actually looks like this. So the input image first goes to a DCT. The coefficients are then quantized. When I say quantized, depending on the quantization level, it can be a lossy quantization. So usually quantization are always lossy, so there will be some loss out here. After that, we have a run length encoding. It's mostly like length encoding, what we do in zip. And then we have entropy encoding to come to a compressed data, which is so we use a coding table out here for entropy encoding. So there are different coding table, and depending on the parameters, we can control how much information is contained on the final JPEG and what can be a loss percentage for JPEG. Now let's come to the video compression. Video compression means video is actually a frame, a series of still images one after another, but they are highly correlated. That's a different algorithm for the video processing. Primarily, the overview is like this. So we remove the perceptual redundancy first by chroma sampling, because as a human we see the luminance more than the chroma. So we do the chroma sampling. We do it in a with higher lower sample rate, such that we get lesser number of bits for that. Then we do the DCT interpretation, so to remove spatial redundance, and we calculate the block motion estimation to remove the temporal redundancy, and then finally the half-band coding and adaptive PLC and all arithmetic coding will move the statistical redundancy. So these are the 4 kind of redundancies that we remove when we do a video compression. So the motion compensation mostly looks like this. The left top is the current frame, and right top is the reference frame. So we need to move which block has moved in which side. So on the left bottom side, we see the motion vectors that has been calculated from the top 2 images. And when we apply this motion vector, so this is the image that we get, that we see on the right bottom, right? That is the motion compared images. So as you can see that it is not at all exactly like the original image how it's supposed to be. So what happened is that after that the error is calculated. What are the difference? Usually SSD is done. Sum of square root difference is done, or sum of absolute difference is done, and then that error bits are transmitted along with the motion vectors for the other end to reconstruct. So these are different blocks out here for the transformation, quantization, entropy coding. This is actually H.264, which is our mbed 4. So if we look at what has happened over the years, 1994 MPEG 2 bit rate and H.264 bit rate in 2003. So approximately we can see that 2x improvement we get in every decade for the compression rate, and this shows the different bit rate and the PSNR values that we have with different kind of compression. So as you can see that we are improving from MPEG 2 to ultimately H.264 or ABC. So here we talk about what kind of application, what is the bit rate, and what are the things, what are the feature set that has been added on different standards. And so this is just information side, not much to look into, but you will see that the BPS rate has gone almost at every stage. So with this background is image processing, we will see what was happening during the 1990-2000 period, and how everything on the image processing side, how it looks like an explosion is happening right now. So the three engines of advancements here. On the computation side, we see we were still at the age of Moore's law. Every 18 months, concentration on the chip, on the IC chip will double, and we have seen a lot of DSPs coming out. On the network side, the communication bandwidth and proliferation of the internet has happened, and along with that, the storage became cheap. So in global scenario, there were also some political changes that was happening. People were coming out, people were mixing. So the communication in a social sense also has increased. So in 1990s, we saw the emergence. Pentium was first available to the consumer. The first engine of this advancement was DSP evolution. What happened during this time is that a lot of chip has gone through series, and what the processing that were difficult to do earlier, that was now being easier. So one emphasis was given to this kind of architecture, where it's a small instruction set, but it has the other features like pipelining and other stuff, such that to make it faster. It has also given emphasis to the vector processing. Actually, vector processing came into this prominence through the graphical processor path. For the graphics usage for gaming centers, all this graphics processor has been developed mainly by NEC and other people, and then this graphics processor has a lot of vector instructions out there and array operations. So those things are very useful when we are doing the image processing. So GPUs are primarily now used not for graphics only, but for all kind of processing, all kind of AI, all kind of vector and array processing stuff. So this is what we are seeing now. There is a tendency of a multi-core processor, and what we are also seeing is that the main processor is the workhorse, but along with that we are having a few coprocessors. Earlier we used to have, if you remember, we used to have a math coprocessor with the chip, but now the trend is going towards that we have different type of coprocessors built inside the chip, such that we have a multi-core processor, and so that's inside one silicon. We are adding some FPGAs, we are adding some GPU capabilities, so creating one SoC kind of thing. Second is that more memory is now available as cache on the chip, so that increases the execution time a lot. And the vector instructions and new use case for GPUs, as I was telling you, that these things are primarily driving the world today for the image processing stuff. So a lot of things on the neural networks that was not being we were able to do earlier. Now we are doing it. The second engine was the communication. Initially, it started with ISDN in the 80s and 90s. Then came the fiber optic as a communication, and in early 90s, I think early 90s or mid 90s, we have the transatlantic fiber connecting Europe with US. So that was considered to be one of the milestones in the communication. And with the communication came the internet. So this is just a glimpse of how the number of users has increased over the period. And if you look at the trend, it is still increasing in that way. So right now we are mostly in the saturation area. So unless there is new applications like IoT or something like that, the number of users in internet should not go much higher than this. And the third important thing about the storage. So earlier, the storage space was costly, and storage space was takes a huge lot of power. As the years have gone by, a lot of research has gone by in improving the storage. Earlier, improving the speed on the magnetic storage with better motor control and more accurate gimbal controls. And after that, from the magnetic, we have moved to the solid state device stage. So right now, the solid state is driving this market on the storage, and the hard drive cost per gigabyte is coming down day by day. So these are the three things: one, the computing power; second, the internet and the communication power as a whole; and third, the storage. These are the three things that enabled us to work with images, which takes a lot of computing power, takes a lot of storage, to possible right now. And when we talk about the millennium, along with that, there came the mobile network. All of us have the mobile network with us now. And if we do not have a network, we somehow feel that we are out of this world. So this has happened over, let's say, last 10, 12 years. This was not the case earlier. And then we have the social media, where people interact a lot. People upload images and videos a lot, and they also the viewership has also gone up. And that is also possible by the commercially available digital cameras. All of us right now have a camera in our hand which is decent enough, takes decent pictures. So all these things has made the things poised for a growth, explosive growth on image processing and other similar processing. This slide shows that how the 2G, 2.5G, 3G, and 4G has improved the speed of the mobile network. Earlier, a video conference we could not think of, but right now, having a conference like this is pretty easy. So, how much time do I have now? Hello?
Sir, yes, sir. Sir,
Yes.
you can continue for 10 minutes and more.
Okay. I will try to finish it up within 10 minutes.
Okay.
Thanks. So in the out here we will talk about the image processing and artificial intelligence. So let's hit the deck directly. First, we need to identify the features. So in a image processing, what happens is that uh, we need to identify the features of the image. We need to then relate the features to some kind of understanding what it is. We may use the features to identify a object, or we may use the feature to relate between two different pictures, and then we do the interpretation and other stuff. So feature extraction is one of the primary things in image processing. So there are three different levels of feature extraction. One is the pixel level or local level, which we call the key point, like finding a corner or finding a particular color, or finding a particular dot somewhere. This is called a key point. A region or patch is something where we find a part of an object or a smaller object. For example, a region or patch is in a face detection. Is your eye will be a region or a patch, or your cheek or your nose will be a region or a patch, where depending on particular corners and particular colors and particular uh, uh, key point features, we will identify an eye in a face. And then comes the global key point, where we have where the use case will be image retrieval. And out here, what we do is that we have the description about the whole image. We like to identify the actual object and what are the relations of the object and things like that. So there are different algorithms that are already available, along with some of them as years uh, when it came into being first. So there are different algorithms out there. Again, those things are still on the algorithm level. We haven't got introduced to AI yet. So I will skip this. So uh, just to highlight that when we identify a key point or a feature, this feature has to be invariant to the scale, rotation, uh, luminosity, all these things. Otherwise, a key which you identify will be different in the two different pictures of the same object. So we would like our keys to be indifferent to, first of all, scale. So there are different scale invariant operators to identify the keys, like shift, sharp, and ORB. And the global description, we have the bag of visual words to describe what this means, to tag a image, and we also have the VLAD, which is a vector of locally aggregated descriptors. These are particularly used. The first we work on the 2D images, and then we extend it on the 3D or a video, the third dimension being time. So we have the 3D variants of all the 2D descriptors and detectors in the 3D domain. Now, this screen is the bridge for algorithmic image processing and the AI. So if you look at the screen on the left side, it earlier used to be the rule-based or the algorithm-based, where the input has some hand-designed program or written program or algorithm, and then we have an output. The next one is the classical machine learning portion, where we define the feature list. We as a programmer, we as a designer define that these are the feature lists you should look for, and we ask the computer to look for the mapping only to identify if those features are available out there. These are classical machine learning cases. In the deep learning cases, the problem happens that sometimes we do not know what those features are. Like when we look at a picture, we do not know. Let's say it's a simple picture of a cat. We do not know exactly what are the things by which we say that it is a cat. But as a human being, we do it every day, and we do it in quite good, almost 100% accuracy. So it must be very easy, but it's very difficult for us to identify exactly what features are this. So then we ask the computer to help us on that also. So we ask the computer to identify the feature and then mapping the features from the input and then say what it is. That is where we are getting into deep learning portion. So machine learning is typically where we say what the features are, but in deep learning we ask the computer, ask the machine to find out what the feature is for us. And then in deep learning, we have two different variants where we have the addition. One is the simple layer of features, and there are some additional layer of features to identify when the things get a little bit complicated. So if you look at the artificial neural network, then it 1950 is one of the very important important milestone in the history of artificial neural network. So this is where the perceptron has been designed first. That was the first learning machine, but that was there mostly on the research lab only. It was not put into very much practical use. Then we have some work, and the interest revived with the advances in VLSI, where when we can see that we can put a lot into a chip, and the chip can now achieve quite a few computation power. So in the meantime, when the theory was ahead of the computation power, the theory has to wait for the computation power to come up to that speed. So there are different types of artificial neural network, and typically they are used for different kind of use cases. So just a few of them which are very important and being worked on right now is that CNN, RCNN, and LSTM. LSTM is long short-term memory network. This is a very interesting thing. Every year there is a ImageNet large-scale visual recognition challenge. So out there, people from different institute, different industry, and different areas, or even as an individual, you can present your artificial neural network, and they will run their standard set of data. They always publish the test data and then run this to find out the performance and which network performs the best. So this is how it looks like as of today. 2010 and 2011 are mostly non-AI based solution. Mostly it was feature extraction based solution, where on the left hand side we see the classification error, which is somewhere between 0.3 and 0.25. That means it was almost more than 70% correct, let's say. But the rest 30% was not correct, was giving a wrong error. And if you look at this, then 2017 looks very promising. So we are pretty much close to be 100%. We may not reach 100%, but we are pretty much close to this. And but if you look at the bottom line also, you will see the number of layers of uh, the neurons in the network that has also gone exponentially. What that means? That means that we need that much of computation power to do it. We need that much of electrical power to run the system, and it may be a little bit slower if the computation power is not that much. So computation, memory, electricity, everything requirement goes up. Some of the applications which are used by ANN, artificial intelligence, typically the CNN thing. One is object segmentation, and another is object recognition. When an object, we have to recognize and localize. First, where something is there, and then recognize what it is. So these are the some example out here where the answers to where and what. This is a very interesting thing. Here, the left top image is the original picture. Then we have picked up the photo of some of the famous artists. You can see Van Gogh, you can see Picasso's images. and then ask computer to draw the same image in the style of different artists. So this is what computer comes up with using a CNN. So let's see how a CNN looks like, the convolutional network. In a convolutional network, what happens is that the main difference is that there is a convolution layer, and then the convolution layer can have, after that there can have another pool layers where it reduces the spatial size and the fully connected layer. So, and this is the example of a CNN, the real life CNN AlexNet, which was the winner in 2012 of ILSS VRC. And these are the different layers. If you look at that, there are 7 layers out here. Barring the output layer and the input layer, there are seven layers in between. And but fortunately, these kind of things are available open source, and we can use, if we want to use AlexNet for our kind of our programming, that we can use it freely. And this is the 2015 winner. Look at the complexity, how it has changed in 3 years. Out there we had 7 layers, and in the 2015 winner we have, there are different versions, 34, 50, and going up to 152 layers of the thing. Our CNN is a recurrent CNN where there is a feedback path from output to back to an earlier layer. So some of the applications are there, that semantic leveling of a sequence or prediction in a sequence. So if you look at that most of the sequential stuff where there is a relationship of sequence, that are preferred by the RCNN, because this feedback loop takes care of the sequential dependency. Also, if there is long-term dependency, then we need to go with the LSTM, where some of the nodes behaves like a memory and remembers the stuff about what happened earlier. So let's look at the trends. One of the things that is happening right now is that in today's world, everything is going towards interdisciplinary research work. And it is not an individual, but a group of people who are doing the research. So it has become a little complicated, and so it is better to approach every problems as a group and involve in interdisciplinary work. Other than that, it's pretty difficult to come up with a really useful thing. It will not be useful in the application domain. It may not have all the checkboxes ticked. So some of the issues that I tried to list out here on this image processing stuff, main issues that you come across out here was that we have developed this kind of complicated nets for solving the problems, but we do not know why this net works better than the other net. Why AlexNet has to be a 7-layer and ResNet has to be 154 layers, and how do you decide that it cannot be 150, it cannot be 200 layers? So there are a lot of work going on out there, typically trying to match the problem statement with the type of network that it has to use. There is also a lot of work going on the looking at the power side of it. Like when we create a computer network like this, the power requirement, as I said, goes high. So they also look at optimization, including power as a criteria. So another thing is that typically one practical problem needs some portion of it to be done on an algorithmic way. Maybe some features we could extract in algorithmic way and then give that to a deep learning system. But there is no hard and fast rule. There is no guideline about how much should be done in the algorithmic way. Where is the partition? So that partitioning between the deterministic process steps and AI process steps, that there is a lot of research scope and a lot of research is happening on that. They are trying to also create some kind of supervisory CNN, which will employ different CNN and take the decision that which one is the best. So there are different ideas are coming up like this. A lot of things, a lot of works are being happening in the super resolution images also, because what we would like to do is that beyond our capability of the CCD cells, we need to go into the super resolution and find more details on the images if we can. Then the interaction between image and text, image and description. I would like to say that I need to see a white, a red flower, and I should be able to find out a red flower image of a red flower from my collection. So, or if I show it some kind of a flower and say that I need something similar to that, it should be able to do that. A lot of things are there already in the Google right now. So the image search, if you have tried it, it works pretty good. But there are some typical images for which it fails miserably. So a lot of work is being happening on the textual to image. So image to text and text to image, both way. Then video scene search. I would like to say that in a movie I like to go to this and this screen the way I describe to a human, and it should be intelligent enough to jump, take me to that position and show me that scene. So this kind of work is happening everywhere now. The other research areas that we are having, the theoretical and the code areas that we were talking about right now. The other areas were application areas mainly, automated vehicle and air traffic control. The algorithm and the research area are more or less same, but the application area and hence the robustness has to be on a different scale for these two. So the automated vehicle, as you know, that a lot of research are going on, and there are quite good progress, but there are still a lot needs to be done. On medical side, the diagnosis side, the treatment planning side, and on the communication between inter-organ signal flow. In these are the three primary areas where people are working. What they want to do is that it's a pure classification problem, where by looking at a radiography image or an image, some image like that, you need to identify, you need to measure and identify. So that is the volumetric segmentation and measurement area. There are different scope of working on the agricultural sector, surveillance monitoring and disaster management. So these are the right now the hot areas where the application needs some kind of intervention. With the availability of drone, the aerial picture, and availability of the space images, the unclassified space images from the space, we can do a lot of image processing stuff based on that. So the scope is immense, and with the power that we have and the tools that we have worked. We have a lot of work to improve on the tool, improve on the applications, and hence it's a very upcoming field right now. So there are some other applications on the consumer area, where the gesture recognition, motion sensing, and some AR application, augmented reality applications are required, especially due to the situation where we cannot meet face to face. So in this case, all these things are required direction where we need solution pretty fast. So that's all I have today. Anything, any question, any discussion that you have, we can talk about.
Thank you so much, sir. Sir, it was indeed a very pleasant learning session. And we have two questions from one of the participants, Mukherjee. Yes. He has asked about how is artificial intelligence is different from conventional techniques of soft computing like fuzzy logic and neural networks.
Yeah, so neural networks is part of artificial intelligence. So what we do in neural networks is one of the tools that we use, one of the major tools that we use in artificial intelligence. If we, it's a very big domain. Uh, Turning portion is all neural networks. That's why I talked about this ANN, CNN, or CNN, all these things. All these things are neural networks. So neural networks is very much in artificial intelligence. About soft computing, other soft computing portion like fuzzy logic. Fuzzy logic is more of a statistical thing, and it has a mathematical base, and it's a deterministic area where we have the, out here it is a non-deterministic thing in AI. Depends on what kind of training that we give, and there is a, yeah.
One more question he is having, that algorithms like vector support machines are also part of soft computing. So what is actually philosophy of artificial intelligence?
Okay, so it's a kind of a different thing, that the vector computing and all these things are computational power. What you do with it is completely different. So when we have the vector computing power, we can do pure image processing, pure graphical display with that, crunching with that, or we can use it for the CNN. As I told that the vector processing power that has been developed as part of display processor. So all the GPUs that we see are meant for display processors, meant to show your screen. It not meant for doing this kind of neural network calculations. It's a hardware that you have. It's a different thing.
Yes. So now we are having a short discussion session we have arranged for you. I request Dr. Mundika Chandan of Electrical Engineering, British Further Institute of Technology, to please share a short token of appreciation to sir.
It is good afternoon, Kallol. It is a very informative talk, and talk will be very much beneficial for the research scholars. So I, Sushmita Dey, Assistant Professor, Department of Electrical Engineering, now present certificate of appreciation for you.
Thank you very much. So it was a pleasure interacting with all of you. I enjoyed talking to you, all of you also. Thank you.
Thank you. Thank you, sir.
So,
was the certificate visible?
No, certificate was not displayed on the screen.
Ma'am, displayed.
Sushmita?
Yes, ma'am. Yes, ma'am. It was displayed.
Visible.
It was
Visible.
displayed, ma'am. It was displayed already.
Yeah, at least I could see it.
Hey, yes, sir.
No, it's visible for all. I think ma'am.
Okay, thank you very much. Now, at the end, I will ask Subhashish Das, who is the who was totally And probably involved of our
I need someone to please turn off your microphone because
Yes, ma'am. Carry on.
yes, ma'am.
question. Cash.
ম্যামের কেটে যাচ্ছে
Yes, yes. I think she's having some network.
Here.
Yes, yes. Shubhashish is there. Shubhashish
yeah I am audible
Dear participants, if you have something to say about this faculty development program, you can share with us. Turn on your video. Please turn on your video.
yeah video is turned on I think I am audible
Yes, you are.
Yes.
Yes, absolutely, Shubhashish, absolutely.
so
You
thanks
are-
ma'am for appreciation for your encouraging words. Good afternoon everyone. We are enlightened by our eminent speaker in the last 5 days with their informative lectures. Thanks to my coordinators, convener and my all colleagues, they inspired us during difficult times when I needed words of encouragement. As a part of the organizing committee, we request participants that if you have any comments, suggestion or feedback regarding our FDP for better events in the future, so you can share your views by opening your mic one by one. So one
all
by
the participants are requested to share your views one by one.
Yes, I would like to say something. I am Dr. Pakisha from Department of Applied Science and Humanities. Can you all hear me?
yeah ma'am.
Yes, ma'am. We can hear you.
Yes. And it was really very, it's all of them. And I really enjoyed the collaborative organization of electrical department faculties. And some of them were highly interesting. And I really enjoyed all of them. And I would like to attend more of this kind of FDPs in the future from electrical department. Thank you. Thank you so much, organizers, for such a wonderful.
Thank you ma'am for
ma'am.
your
Thank you
encouraging
very
words.
Thank you, ma'am. It's our pleasure.
Next, I like to Yeah. Yeah. Good afternoon, everyone.
Good afternoon, ma'am.
Good afternoon. Thanks everyone for keeping briefing on such emerging topic. Really, it was a wonderful journey of 5 days learning. I am very much thankful to my supervisor, Professor T.K. Basu, who had given me this chance to attend your FDP. So really, it was a wonderful journey of learning in sensors, automation, and its application. Thanks a lot. Thank you.
Thank you, ma'am.
Thank you, ma'am. Anyone? Yeah, welcome. Sneha, she's to say something.
Nandita Ranjana ma'am is there.
Yes, Dr. Ranjana Goswami, you can also say a few words. Please unmute your microphone.
Yes, Nandita, it was really, I was thinking before participating that really how much I will understand coming from the Department of Applied Science and Humanities and Physics. How much overlap will be there regarding what we really work with and what I'll be attending. But then I realized after attending the conference that the world has really become interdisciplinary, that we really understand what others are saying and how everyone interacts and how everyone needs everyone's help in all spheres. that was really very informative. Some of the presentations I found very much to my heart, and I really liked it very much, Nandita. And every faculty members of your department, they did wonderful job. I must really thank them for working so hard, including you.
Yes, definitely,
It was
definitely.
great. It was really great.
Thank you, ma'am, for your encouraging words.
Some research scholars are there. If you want to say something, you can say.
Ujjwal Dev, will you?
Mr. Gopal Chandra Dev, Ujjwal, they are just I see.
Some research scholars are there. If you want to say something,
Kushal?
you can say.
Yes, madam.
Yes, yes.
Hello.
With us.
Hello.
Experience.
Yes, Nyasis, you are audible. You can share your views.
Yes. There are connectivity issues, so my voice may break.
No, it's absolutely
Yes,
fine.
all of
Okay,
our
okay, okay, no issue. You can carry on.
It was very nice because I was a student of the college where I am now taking of FDP as a faculty. It is a nice experience. Obviously, the discussion will enrich me and have enriched me, activate my career in few aspects, especially the session that was discussed on the last day, how to write technical papers and those things. I found them very useful. Thank you for organizing this thing, and thank you for granting me to take part in this.
Thank you, Snashish.
Nandita, Mr. Gopal Chandra Dev is there. He wants to share, I think so. Mr. Gopal Chandra Dev.
Thank you. Democracy, he has
Good afternoon, madam and sir. Hello.
Yes, you are audible,
Yes,
sir.
you are audible.
Yes, this is audible now.
Yes.
Yes.
Actually, this is really good program for conduct since last 5 days. So this is very good session, and we learn very much things from your every program.
Thank you.
Thank you, sir. Thank you.
So, now we have come to an end. So, Principal Madam, present here, D.N. Chattopadhyay sir, members of different colleges, and my colleague, I am extremely happy with this constituencies after this national FDP on census information system organized by Electrical Engineering Department. More than 140 participants from 41 colleges all over India participated in this activity. I thank you all, Mrs. Sabi, the part organized. I would like to give thanks to our invitation, shared their knowledge. Thank Principal Formatter College, I thank Mr. Chakraborty who got their spirit. Also, Ms. Sonush, Mr. Auditor Ghosh for very efficient management of each day's program. Organizing committee members Chandrani Das, Madhumita Kundu Mandal, Jata Shaha, did a praiseworthy job in updating the participants with every mindful information. I thank them all. Sushmita De, Arko Kamal Pal, and Subhashis Das incredible job in designing the website, e-planner, and also very importantly, they webcasted the online program in Google and YouTube. You will there are 232 viewers maximum from core of my heart. We have there is a feedback form every day. Participants who have filled it up. Third section of technical quiz, and all of you participated in that quiz. And Sushmita, please share the screen. There are 10 participants who have scored full in this technical quiz, and I congratulate them all. I am all of them have well in this quiz, and hope you will it will be again attending our college when we will again organize it. I expect participants please share. Sushmita.
Ma'am, it is already shared. Already shared, ma'am. Everyone can see that.
Yes, ma'am, it is shared.
These are the top scorers, and all of you are the top scorers who have participated in this event. I expect the participants be a research scholar or a faculty member to extract the whole essence of a smart system from this FDP. And as an outcome, we will expect very good publications in coming years. I like the congenial atmosphere developed between participants, faculty members, organizers, speakers. This, I, Nandita Shanna, signing off with an English translation from a word from Aitareya Upanishad. Move constantly to collect honey, but or fruits, and the sun is perpetually emitting light. So, keep moving for thirst of knowledge. Thank you.
So thanks a lot all the participants for your motivation and for your participation here. Now I would like to request all of you to kindly fill up the feedback form, and after that the certificate will be dispatched to your the link will be dispatched to your mail ID as well as in the WhatsApp link, and we will take 2 to 3 days to upload that. Kindly check into it.
Thank you.
Turn on the video to take a photograph.
Please turn on the video. We have a group photograph. We have a group photograph. Please turn on the video. We'll have a group photograph.
Devashi, turn on your video. Sarji, turn on your video. Alim Sheikh, please turn on your
Load shedding.